Hello. Very happy to be with you today. I'm Dr. Terry Chambers from the University of Louisiana at Lafayette, and I'm the director of the Energy Efficiency and Sustainable Energy Center here. I'm joined by my colleague, Dr. Carrie Ritter, who is the director of the CLECO Alternative Energy Center and also the director of our VR application development group. Today, we'd like to talk to you about virtual reality applications for solar energy education. And we'd like to begin by just giving a brief overview of the solar energy and virtual reality work that we have going on here at the university. And then we'll go into the new VR work that we've been doing. We've been doing concentrating solar thermal research here at UL since 2012. And this facility that you see right here is a concentrating solar thermal power plant. We have about 1,000 square meters of reflective parabolic trough surface area. And we have that test loop connected to an organic cranking cycle turbine that produces 50 kilowatts of electricity. We also have thermal energy storage at the site, which we're actually just completing the installation of that. Inside the building, we have 3 biomass projects: biomass gasification, torrefaction, and digestion. At this same facility, we are currently in the middle of an upgrade to convert it to a microgrid test facility, and we'll be adding another 50 kilowatts of photovoltaic and battery storage and EV charging, and all in a microgrid environment, such that we will have simulated sources and loads, so that we'll be able to simulate any type of generation profile and any type of load profile and identify what the effect that would have on a local feeder of the utility grid. Next. Some of the work that we've been doing there over the years includes numerically modeling the system very carefully so that we can characterize the performance of this type of technology here in Louisiana. Testing different types of reflectors to see which works better, including which is more resistant to soiling. We like to work with companies who have products that they need to have tested, and they can test them in our facility. So one company came up with a low-cost receiver, which you see in the upper right-hand corner there, and we tested that. We also have tested a concentrating solar photovoltaic device for a company, and also we've developed our own autonomous SCADA system and have worked on solar resource measurement and forecasting and power forecasting and so on. We also have at another facility, we have what we call the Louisiana Solar Energy Lab, and at both facilities, we use those not only to make power, but also to perform solar energy research, education, workforce development, economic development, and outreach. And this is a 1.1 megawatt applied research and testing lab where we have extensive outdoor test facilities, and also where we can test all different types of solar technologies side by side. Here is a zoomed in picture on some of the test stands that we have available to us here. We have dual axis tracking, single axis tracking, simulated residential roof with battery storage, simulated commercial roof install, bifacial module test stand and concentrating photovoltaic, conical dish photovoltaic test stand, as well as an advanced meteorological station. And in addition to those test stands, we also have 1.1 megawatts of solar modules of the three different primary types: thin film, monocrystalline silicon, and polycrystalline silicon. And we test all of those to see which type works best in Louisiana. And that building that you see there at the corner of the solar field, that is our new laboratory building. And that's where I'm sitting right now. And in that laboratory building, which is 4,200 square feet, we have some very sophisticated indoor test equipment also, where we can control the test conditions when we're testing these solar modules. Some of the types of modeling that we've been doing, modeling and characterization, is to, as I mentioned before, to determine which of all these types of solar modules work best and are most cost efficient in our climatic conditions. And it turns out that in our area, that the thin film modules perform the best and are most cost effective. We also have a very nice virtual reality laboratory, and we use the VR technology in our VR lab. Could be used for any domain, but what we primarily use it for is for solar energy education and outreach. So we do have a very nice laboratory where we have a cave automatic virtual environment with 3D projectors, which is the picture you see in the top right there, and full body tracking so that visitors can stand and walk around in the virtual environment. We also have head-mounted displays that we also use, and we'll talk more about that. One of the first applications that we developed for engineering education was a model that it was an application that modeled the concentrating solar thermal power plant and explained to the users how they could or how it worked. And one of the great advantages of virtual reality compared to just a PowerPoint or a slideshow is that because the user is immersed in the scene, they can experience the size and the scale of the facilities, almost as if they were actually there. So that's one thing that's nice. And another thing is that they're able to, through virtual reality, visualize things that they would not be able to visualize, such as the flow of the working fluid in the turbine. Another application that we developed was what we call PVVR, for photovoltaic virtual reality. That was a training program to provide introductory training on photovoltaic technologies. And there is a virtual instructor that provides visual and vocal interaction with the students. So that little robot that is hovering there in some of those pictures, that is the virtual instructor, and it can talk to the students and provide them instructions. The model consists both of CAD models that were brought into the VR environment and also 360 panoramas, 360 photographs that were brought in as well. And there are various animations that help explain solar energy concepts and PV system components. And there also are some learning activities embedded within the application. And as the students interact with those learning activities, there is a built-in assessment that helps us to understand how well the students are progressing in their learning. And now I'd like to turn it over to Dr. Ritter, who will talk about the latest VR work that we've been doing, led by him, by the way.
Thank you, Dr. Chambers. Yes, it was important to kind of give you an introduction to our actual solar facilities before. One of the, I guess, primary initial purpose of creating our virtual applications was to reach more people. We have these amazing facilities here, but not everyone can visit them in real life. But with these virtual applications, not only can visit them through virtual tours, but you also can make them interactive and educational. So just a little, I'm going to give a brief introduction about virtual reality, and then I'm going to move on to our main applications, and then the last study it published, and the current one that is being published so far. So just to let you know, virtual reality training is on the rise. Just in publications, in 1998 there was 6, and in 2018 there was over 213 on specific VR training, and they kind of give you ideas of all the advantages in cost, safety, convenience, spatial, visual understanding, retention. And the main fields that they are directed towards have been manufacturing, medicine, military, and also education, which is what we're doing here. And lots of different fields in use, such as prototyping, assembly, drive, flight, and surgery. So it's definitely on the rise. And the industry is actually predicted to go up to 1.5 trillion by 2030. So it's rising exponentially. And it seems there's a convergence as we increase the processing power of our virtual reality headsets and the resolution. And it's going very soon. We're going to have 16K headsets, which is what we see in, and so there's going to be no difference between what you see in the headset. So it's assuming to rise. Once that happens, which should happen in the next few years, it's predicted the industry is going to just balloon. So one issue we have is the dropout rate in engineering is over 40%. And the main reasons have been with difficulty in the subject matter, mismatch between teaching and learning styles, and people don't have a connection. And the learning content could be considered quite difficult in the concepts, and they're hard to be conveyed with traditional methods. And so the hypothesis that we're offering with this lab is to use alternative methods such as advanced visualization techniques and put them into virtual environments and to motivate and engage students to learn complex engineering content. And we're hypothesizing this will result in higher comprehension. So I'm going to go through a couple of completed applications. As Terry mentioned, our first one was the Virtual Energy Center. So this is a scale model of an actual concentrating solar power plant we have in Louisiana. The focus had been to motivate, engage students, and we perform virtual tours. We could even do remote virtual tours, and we teach engineering concepts. So our power block is an organic Brinken cycle, and so it's a mechanical engineering cycle, and we're able to explain all about it, which I'm going to show you in a minute. So a little bit about the development. So we had actual scale drawings of the facility. We modeled it in SolidWorks, And then we imported the model into 3ds Max Design. This allows us to put very detailed textures into the model and make it look a lot more realistic. Then we import it into Unity 3D. Unity 3D is the game engine we use to develop our virtual reality training applications. And for visuals, we use either the Oculus. We've gone through every Oculus model thus far. Now, of course, they're using the wireless headsets, which are a lot more convenient and a lot less costly than the original ones. And we have track remotes. And also for the teacher, we use a Microsoft Connect that actually captures depth and color, and we're able to project that onto a mesh. And you can you see in this picture on the bottom right where it actually looks like you're interacting with the teacher. So I'm just going to show you a little video of the actual application. So initially, the user starts in an overview area where they can see everything. We slowed down travel to decrease motion sickness, as moving fast in VR was shown to give users an uncomfortable experience. In this application, you get a much better idea of the relative sizes of things. So the collectors in front of you have an 8-meter aperture, which are closer to 30 feet tall. There's in-game assessment that we use to help reinforce learning, and it gives you, and there's lots of interactions as well to kind of engage the user in the experience. One advantage of VR, we could make things translucent, and you could see different flows. We could also slow down fast processes, so the user can see actual stuff going on, such as here, where we have mechanical processes where we slow down the expander the users can see how the gas can turn an expander, which then turns a generator and generates electricity. So in this, we're explaining how this cooling method condenses the refrigerant back into a liquid, and then that's basically the end. So that was our first application. We completed that in 2016, and we presented that in many different conferences and as well. And so then shortly after, we built our photovoltaic lab, and we started this second main application, which we call PVVR. And we actually modeled the entire solar field down to the DC optimizers you see in the bottom left, and every single module and everything was completely modeled for this application. And it's a model of the plant you saw earlier, or 1.1 megawatt Louisiana Solar Energy Lab. So a little bit about the development. As I mentioned before, we use Unity as a primary game engine. For this, we also use Audacity as an audio editor. For the 3D graphics, we use SolidWorks, Maya, and Blender. And then of course, we use the Oculus, primarily the Oculus Go, which is the mobile version for display and control. So as mentioned, we do have a guide. We call them Visor. It stands for Virtual Interactive Solar Instructor Robot. So this guide initially gives users an introduction to VR and controls. And I'm going to show you So this is a 360-degree image that was taken from a drone so that the user could view the entire environment. And then we animate objects, and this is explaining the solar resource that we receive on Earth. It takes 8 minutes for photons of light to reach us on Earth. All our applications have an initial training program where you can learn the controls, and we try to make them as simple as possible, such as single button controls. In this application, he's wiring. This is a series and parallel wiring application where the user is learning how to wire photovoltaic modules to a junction box and inverter in order to receive the correct voltage. This is another training program where for complex interaction, the user is shown some initial training. And we also would show 2D videos so that to help with the training. The idea is to have the user not need any help from the trainers and just be able to complete it all himself. And so in this components application, the user's grabbing the different components, assembling them on the display in front, and then they're tasked with wiring them together. And there's different type of wiring types, and once they're done, they perform a check, and so for this application, the complexity of each would increase but users were given a training program, and then they were able to actually wire in very complex systems, and it worked successfully. We also employ game-like interaction. We noticed that it's been shown that this increases engagement and motivation. And so I've just kind of shown you the general or learning environment of photovoltaic PVVR, photovoltaic virtual reality. And so this was a study that was completed and published in 2021, and it's where we compared different techniques of learning. One technique was to use 3D modeled environments, and the other, and compare that with 360-degree panoramas. And we used a university graduate and undergraduate class in a solar design class. So the students were actually learning about photovoltaics and design in the class, and then this was actually a supplement for the class. So they had a semester of class, and they toured the facility, and we used Oculus Go headsets, and where we could test many students at a time. So here's the, as you had seen before, it's a 3D modeled environment. We have, initially we kind of showed, explained how photovoltaics generate electricity. And then we also have our solar resource measurements and our energy conversion devices. So this is the 360-degree photo environment. So yeah, this is 3D modeled. Everything's modeled in 3D, and then now we have the same environment, but it's just photos. So results from that study in the 360-degree. So we did pre and post tests, and in those results, the 360-degree, they had a 13% improvement versus 1. But we also look into the normalized gain, which the normalized gain takes the improvement independent of the pre-test score. So regardless of how good you do in the pre-test, you could still see what your gain is. And the 360 degree far surpassed the 3D model. So in conclusion of this study, the students were overwhelmingly positive with enjoying virtual reality training. There's much higher test results with the 360 degree panorama. And so we conclude this is more effective, and it's also the quickest to develop. 3D modeling actually takes quite a long time to model out an environment, and it's also more computationally expensive on the processing power when you're using the headset. But 360 degree solves a lot of those issues, and they also solve other issues such as your static vantage point and stitching parallax, which can cause some dizziness and issues with your frame rate as well. Can cause a less of a user experience. So 360 was the clear winner in this study. And we used the mobile headsets, the Oculus Go. These were much more cost effective. And it's for doing demonstrations, the setup and breakdown time was much quicker. And it allows us to test an entire classroom at once. So the next study that was actually, it was conducted this year, and we actually just put the results together, where we compared a two-dimensional symbol environment with versus 3D models of electrical components used in constructing photovoltaic systems in different VR environments. So our testing group here was graduates and undergraduates in mechanical engineering and in engineering technology class. And again, we used the Oculus Go. So the aim of this study was to compare different visualization techniques to train participants in the design of PV systems and the increase in complexity. So the initial one was just a PV direct system, which is just basically solar and then a load. And then it went all the way to a grid-tied PV system with battery backup, which is quite a complex system. So these are all the different components that the user had to pick from. And these surrounded the user in 3D, and they would turn one way or the other and pick a component and then put it on the board. Then they had to string the components together using DC or AC flow. And these show the actual flow going from one component to the next. So this is the mixed reality environments. One was on the left, that's our 2D photovoltaic environment using symbols. As you can see, this is actually just the initial training part where we showed you what a PV direct system was. And then on the right, this is building the system in the 3D environment. And so all the components are 3D models instead of symbols, and you're stringing them up in a 3D environment in the actual photovoltaic lab outside. And I mentioned before, for the wiring, you actually go to the left side of the screen there, you pick your AC, DC, and then you pick your type of, whether it be unidirectional or bidirectional flow, and you can wire in the system. So for this, again, we use quantitative and qualitative measures to gauge the effectiveness and the participants' experience. We use pre and post tests for the effectiveness, and questionnaires were given after the application to test their experience. So this is some of the results overall. We have the improvement and normalized gain again. And as I mentioned, normalized gain is the improvement independent of the pretest score. 3D showed a 0.29, which was 25% higher than the 2D. So 3D seemed to be the application that users learned more from, but to look more closely than just that, we broke up the participants by first gender. There was 51 participants, and it found that there was only 10 females, so only 20% were female, but the females seemed to do a lot better with the 3D at 15% higher with 0.35 or 0.11, whereas the males were only 10% higher. And then we also looked at breaking them up by age group, and it found that 18 to 21-year-olds scored a lot higher on the 3D, actually 140%, 0.56 versus 0.22, and whereas the 22 and older actually scored lower on the 3D. But overall, the 3D was much larger. So then we also looked into the current experience of the participants, such as video game, educational game, and virtual reality. Students were asked if they had much experience, no experience, or some experience in video games, educational games, and virtual reality. And just to note, only 6 and 10% had a lot of VR and educational game experience, but 57% had much video game experience. So most of the people we tested were active video gamers. So some of the results of that, out of those 57% of gamers, so the green here is 3D gain. They had a lot more gain on the 3D application than the 2D. Whereas if people with this is another one, 57% said they had some VR experience, and here the applications were quite similar, only a slightly larger gain. And this is just showing, this was just another way to break up the results and see if there's any large contrasts among them. So now we look at the qualitative results, and this blue over here is the 3D model, and as you can see, they far surpassed the 2D, which is shown here in the brown, in almost every single category. And the questions were, which gives you a stronger spatial understanding, which is more conducive to learning, which is more captivating, which is more comfortable, increased peripheral awareness, stronger sense of being there, and which one would you rather? 80% would rather the 3D model, and then on every category, the 3D modeled far surpassed the 2D, except on the distraction. So they did the 2D with the symbols and the wireframe mesh was less distracting than 3D. But other than that, 3D modeled was high. So in conclusion of this study, the 3D was preferred with 25% higher gain overall. The females were 250% higher compared to the males with 10. The younger age group had a much higher preference for 3D and scored higher in the quantitative results. In the qualitative results, as I mentioned, 3D was substantially higher in every category with 80% preference over the 2D. And the only main negative comment of using these 3D was that it's more distracting. So discussion, these type of environments provide an opportunity for education without being exposed to any dangerous situation, and it eliminates a lot of costs required to bring people to a training center. In fact, it opens doors for anyone to virtually visit our facilities and to learn about them. And it has been shown that this full immersion allows deep learning, more retention, and it could be much less distracting than traditional learning. So I do have a list here of recommendations. These are recommendations for anyone who would like to develop virtual reality applications for education. One, animating products and processes for explaining difficult concepts. Showing animations while explaining in VR has been shown to increase your users' engagement and captivation, and they also comment on this being one of the highlights of the experience. In order to mitigate motion sickness, rather than having users be able to travel in the environment, it is recommended to use some type of teleportation. We had initially, when the processing power was much lower, our frame rate was lower as well, which generally you want about 70 FPS to have a comfortable experience. But our frame rate got below around 50, and so that made the walking much more prone to motion sickness. But now as frame rate keeps increasing, this might not be an issue anymore. But we're still, for right now, travel, we just do teleportation. For testing environment, initially we were using the headsets that were connected to desktops, and so we only could bring between 2 and 4 for a testing application. And if we set them up in a classroom where other students were and they were talking, we noticed there was a much strong decrease in students were much more distracted. So the optimal testing environment should be a quiet room that's completely free from distraction. And then initial training program to equate users to the immersive environment. We found a lot of times users would put on their virtuality headset, and those who have never used one before, and they'd be so captivated and interested, they would just look all around, and they weren't paying attention to the education part. And so the whole initial part that we're trying to explain that they would miss, just because they wanted to look around for a while. And so, and then there was issues with controls. Some people who aren't experienced in video games or educational games, that they had issues with controls. So we added initial training programs in our application, so users can, one, get acclimated to using the virtual reality, and two, to learn about how the controls work. And as I mentioned, we try to use one button controls. For those not acclimated to VR or to video games, having multiple buttons on the controller, it was very difficult for them to learn sometimes, and so having extremely simplistic controls and a training program seemed to be the best environment. So this was our 10th virtual training application. So these are recommendations from not just one. This is a kind of overall recommendations. But for our when networking, when you have many students join a virtual training environment at once, we found that they shouldn't be able to see each other, because when a lot of them are together in a classroom and you could see other students moving around and looking around, it caused more distraction. And so we assessed long-term retention, which this is this has one strong advantage of virtual reality over traditional, is where you test participants a week or more after the application, again on retention, and we found that virtual reality had much more long-term retention advantages, and this could be looked at as in that the virtual experience was much more captivating than the traditional learning environment, and this higher degree of captivation allowed more long-term retention. So a little bit about our assessment techniques. We've measured the improvement in learning outcomes, and then we compare effectiveness using different techniques. And the techniques that were for our last two studies that I presented here today were between different learning environments, such as 360-degree panoramas versus 3D model, and then also different visual techniques, such as using 2D symbols in a wireframe mesh, a very basic environment, versus a 360-degree in the actual environment, or in a 3D modeled environment. Oops. So here is just some of the testing pictures. This was a industrial or a programming class for a controls class, and these low-cost headsets allow us to buy enough headsets to test the entire class at once. This has many advantages in that, I had mentioned before, if you have half the class or a few students, then testing the other students or the testing environment can be distracting. But testing the entire class at once was shown the most effective. Plus, we're able to get a lot more feedback from the entire population. This is a thermal fluids lab class, and we also were able to test the entire class at once here. So initially on the board there, I would show I do show a PowerPoint explaining the controls. The controls are also explained in the environment itself, but just to reinforce education, I would show that. And as you could see, the students have in front of them a piece of paper. On that, they would complete the pre-test, and then they'd flip it to the post-test to complete the application. This picture was actually published in the university paper, and that's all. Do you have any questions?
Presentation, we have some questions and comments from the attendants. The first one is for the analytical part of the course, such as energy balances and energy calculations, which are taught in the classroom. How do you link them to the virtual reality excursion?
I'm sorry. How do we link what again?
How do you link the energy calculations and energy balances when the students go from the classroom to the virtual reality excursion?
Yeah, so we teach the concepts and the actual calculations in a regular classroom setting, and then these are what we would consider to be learning modules. So when they're learning just the concepts that are in this application, we let them do that in that application, and then we teach them the other things. Mostly the calculations are taught in a regular classroom setting. So we have not studied the learning of engineering equations in the virtual environment yet.
Okay, thank you very much. For Dr. Chambers, is the energy produced by the solar cell pilot plant used in the university facilities?
Yes. Actually, the facility that you see on the slide right there, that's our 1.1 megawatt solar facility that is on campus. And this is used to power the south part of our campus. Okay. And we produce about 20% of our annual energy needs from this solar plant. The other facility is sponsored by the local utility company, and the power from that goes straight back to the utility company.
Okay, thank you for both speakers. Do you have any grant from Louisiana government, National Science Foundation, private companies to develop these facilities?
Yes, we have had all of these facilities have been developed using grant funds, and primarily from industry, but also from the Department of Education. And Carrie, I'll let you mention the funding for the VR part.
Sure. I guess the initial funding, we had a National Science Foundation funding for the first concentrating solar power plant environment virtual energy center. Then we got a Louisiana enhancement grant that helped us. We were able to buy new computers and virtual reality devices with that. That's an equipment only grant. And we received a Mozilla fund where we were able to purchase mobile headsets, and we did mobile applications. Then we received another enhancement grant in collaboration with an educational professor, where we studied renewable resources for virtual resources with that. Currently, we're going for another National Science Foundation grant for virtual training development, which virtual manufacturing lab development. So we virtualized working in a manufacturing lab, which such large tools such as a lathe and a mill, a CNC machine, where students can learn how to operate these machines, which gives a great advantage in that you could only have so many of these large, expensive machines to train students, but virtually you could train as many as you want. So it's many advantages to save cost and time in initial training.
Okay, 2 questions for Dr. Ritter. Are your products intellectually protected?
Are my products protected, you said?
Yes, by a patent or copyrights or something like that.
Not at this time. The applications, I guess if you were interested in collaborating, you're welcome to email me. We've shared some of our application content with others, and we're trying to help each other, build. And I'm always looking for collaborations. So no, we haven't patented or any of these applications. We mainly just use them at the university and conferences.
Okay, another question for you. Will be your VR platforms available for sale?
Wait, VR what available for sale?
Will be your virtual reality platforms available for sale?
Our specific ones?
Just for example, one of the examples you have shown, is it available for sale for a company or?
Okay. Well, no, we haven't sold any. Again, though, if you're interested in previewing them or whatever, you're welcome to reach out to me, but we have not marketed these for sale yet. I don't think they're in a we have actually we are looking to collaborate with industry to make virtual training for them. In fact, when I mentioned our virtual manufacturing training, I reached out to manufacturing companies locally to collaborate with them to develop specific training applications for the company. So that's we are looking to network with companies and in industry for that. But our main applications were developed from grants to just study different training applications and techniques and to publish and disseminate in that way. But we haven't partnered with we haven't received a grant with industry partner to develop specifically for their training. But I do foresee that happening quite soon, especially with the increase in processing power, allowing for more comfortable viewing and VR training. And in fact, I have another slide I didn't show, but virtual training has been being used by giant corporations all over, McDonald's, Walmart, and then there's a big sports market that we've collaborated with a local virtual reality company to train our football team in using virtual training applications, such as the quarterback, where he could review plays and see and possibly see different options to use during that play, and that's also being used. In fact, the Saints, New Orleans Saints, which is our Louisiana football team, our main quarterback, Drew Brees, used virtual reality training to benefit him.
Yes, I think the work you have made until now is for teaching purposes mainly. So, and two final comments from the attendants. You have made a very nice work. However, I believe that the experience of visiting a real plant is irreplaceable. And finally, congratulations to both the speakers for their contributions to teaching, research, and technological development. And
thank you.
From my side,
since you say that visiting a real plant is a very valuable experience, I invite everyone to come to Louisiana to visit our facilities.
Okay, thank you very much. I really enjoyed your presentation. I learned a lot, and I will visit your facilities in Louisiana. Please be sure. And thank you very much, both speakers, for very nice presentation. And we keep in contact. Thank you very much, and have a nice afternoon.
Thank you.
Bye-bye.
Bye-bye.